All right, so this is part 2 where we are looking at the quantum mechanical model of our atom. And we finished off in our last video in part 1 looking at the Bohr's contribution. Now, Bohr did a lot of things about amounts of energy being released from the atom by the electron and the line spectrum. And basically, what Bohr's main findings were is that he comes up with the Bohr quantum model of the atom. And this model of the atom is a mathematical formula used to determine the maximum number of electrons that can be placed in an energy level. He did a whole bunch of other things where he talked about that the energy is actually behaving like a particle. When it's released in little packets instead of a continuous wave, which actually prevents the electron from crashing into the nucleus and losing energy. But for us, he's the guy who determined that based on energy and mathematical formulas, he was actually a mathematician. He figured all this out using math, which is crazy. He's the guy who comes up with the fact that there can only be 2 electrons in the first energy level and 8 in the second one. And things get a little tricky in 3 and 4, and we're going to learn why as we move through this unit. Now, so this model gives us our visual of how electrons are arranged through the atom. It's telling us how atoms are structurally different from each other. So our nitrogen is different from our phosphorus because they have different amounts of electrons, and phosphorus has a 3rd energy level. So Bohr's model helps explain a lot of trends in the periodic table. It explains our valence electrons, common ionic charges, those trends that we talked about in 3U, ionization energy, atomic radius, stability of noble gases, electronegativity, all those things. So Bohr's model was really good in the fact that it explained all of these periodic trends that we analyzed in depth last year. The problem, actually, if you want, you can pause this lesson and you can recap the Bohr model by looking at the video that is in your slides and also in your HyperDoc. The problem with this model is it still doesn't tell us where the electron spends its time in the atom and how the electron behaves in the atom. Because Bohr only observed hydrogen, which is a one electron system. His theory actually did not work for multi-electron systems. And so that is kind of the flaw in Bohr's theory. His solution to the fact that it didn't work in multi-electron systems is that the electron orbit doesn't obey the law of physics. Ms. Easton is probably going to have something to say about that. So Bohr's theory was actually really flawed because it only worked for hydrogen. Even though it explains all the periodic trends that we talked about, it's kind of sketchy. Okay, so along comes de Broglie, and he has this hypothesis. Now, Bohr's theory was based completely on the fact that light can behave like a particle. And so de Broglie wondered the opposite. If a wave can behave like a particle, then a particle should be able to behave like a wave. Remember, prior to this, particles and waves were like separate entities. What he did was showed that a beam of electrons would diffract like light when passed through a barrier. So I want you to think about this. Right now, when I'm recording this, it's a beautiful, nice, sunny day. So the sun is coming through the window, and the light is diffracting, which means when it's coming through my window, it's bending a little bit, and then the ray of light on my floor is not straightforward from the window. It's actually bent a little bit. That's diffract. So light diffracts when it passes through the glass of my window. And so what de Broglie did is he shot a beam of electrons through something like a window, a barrier, and it also diffracted. This is huge because now it's showing electrons are behaving like light. This means that electrons aren't particles, but they're wave patterns. Again, you might want to hit pause on this video and go and look at the de Broglie recap video that's in your slides and also in your hyperdoc. So after de Broglie, Schrodinger comes along. Now, he did a few different things. He did some stuff with a cat. And he has this uncertainty principle he kind of contributed to. But now, if you don't know what Schrodinger's cat is, you can hit pause and look that up later. Now, Schrodinger says, okay, you say electrons are a wave, you say electrons are a particle, let's figure this out. He says that electrons are actually moving in wave-like patterns as they orbit the nucleus. So instead of orbiting the nucleus, if my fist was the nucleus, instead of orbiting the nucleus perfectly like this, he's saying that they're actually doing wavelength patterns as it goes around the nucleus. So there's some couple rules with this Schrodinger's thoughts here. He says that only certain wavelengths of light are possible based on the circumference of an orbit, because our wavelengths have to perfectly line up. They're not allowed to interfere. So if you look at the pictures on the slide, in blue, the wavelengths perfectly lined up. So it's a continuous, it goes continuously around the nucleus, and the wavelengths don't interfere like they do in the red. So the reason electrons in different energy levels had different amounts of energy is because their wavelength patterns around the nucleus have to be very, very specific. So the bigger the orbit they're going around the nucleus, they're going to have a different wave-like pattern as it orbits compared to a smaller orbit, because they have to perfectly line up. So after Schrodinger comes Heisenberg. Heisenberg has this uncertainty principle, and what he says is, wait a minute, okay, it's not possible to know both the speed and location of an electron. He said they're moving around way too fast. The more you know about the location of the electron, then the less you know about how fast it's traveling. So what we can do is we can only know that an electron is within a region of space. We know that it's in a specific area. So there's flies on my screen. But we can't know its specific exact location and its exact speed at any given point, because once you calculate one, the electrons moved so quickly you can't possibly figure out the other one. So this is what results in the probability model. So our probability model of the atom, because it's impossible to know exactly where an electron is, we describe instead the probability or likeliness of an electron being found in a certain position around the nucleus. So again, because we can't know exactly where it is, we describe the probability of where the electron is. So where do we think it probably is? So electrons, again, contained in our energy levels, we know this, they're called orbitals. Now, these orbitals are not the orbits described by Bohr. The orbits described by Bohr were that they're in very specific distances from the nucleus based on the amount of energy that they have. The orbital, similar word but different, the orbital is described as the area of probability of finding an electron. So the orbital is an area of probability where finding an electron is high. Orbit by Bohr, very distinct distances or energy levels from the nucleus. Orbital, area of probability we're going to find an electron. Okay, we can't know exactly where it is, but we can have a good guess. And so the orbital is the area we are likely going to find an electron. So that brings us to our fuzzy atom idea. Now, the fuzzy atom idea is that the darker it is, the higher the probability we're going to find an electron. So nice and close to the nucleus, we're going to find more electrons there than we are further away from the nucleus. And this is because the further you move away from the nucleus, the more space is available for the electrons to occupy. So the orbitals get bigger, and thus you have more space to look for the electron to occupy. It's like my kids. If my children have to stay in the playroom, I'm going to find them really easily. They're going to be there. But if I let Daniel explore my entire farm, he's got 200 acres to explore, there's a less of a probability I'm going to find him when I go looking because there's way more space he could possibly be occupying. So again, you can hit pause and you can watch this video where it talks about the fuzzy atom idea. And then this is just a picture showing the difference between the Bohr atom and the de Broglie atom. So the Bohr is like very neat orbits around a nucleus, and then things get really odd with the de Broglie atom, and we're going to look at those orbitals in more detail coming up in a couple more lessons. Okay, so this is the end of the quantum mechanical model. I know it's a lot to look at. There are some other videos in your HyperDoc to help explain things and review the concepts, and I'm really going to suggest that you look at those.